Okay, two more methods for the advection equation. We are still struggling with the same things, but as you can imagine, over time people have evolved different numerical methods. After one method is evolved and it's found to be unstable, somebody tries to take the good points of it and try to correct the things that either make it unstable or diffusive or dispersive or whatever. So you end up with schemes, modified schemes, but still you are not getting away from the basic issues of numerical accuracy, stability, and the tough choices you have to make on the time step and the spatial steps, right? So Lax Wendroff scheme basically tries to build on what we did before. We looked at forward in time, so Cmn plus 1 equals Cmn minus u delta t over 2 delta x, Cm plus 1 n minus Cm minus 1 n. So centered in space, forward in time, and we found this Euler forward in time with center space to be centered in space to be unconditionally unstable. So what Lax did was to then try to average the previous time step to see if we can add some stability to the Euler forward scheme. So it is still a forward scheme. Cm n plus 1 is 1/2 of Cm plus 1 n plus Cm minus 1 n, and then this term remains minus u delta t over 2 delta x times Cm plus 1 n minus Cm minus 1 n. So it is apparently still centered in space and forward in time, except that in forwarding the time we have spatially averaged here between the 2 points around m for getting the previous time step. What does it do? Essentially it amounts to still being the Euler forward, same as before, plus an additional term which is 1/2 of Cm plus 1 n minus 2 Cm n plus Cm minus 1 n, which is essentially a diffusion term. So term D can be written as using Taylor series expansion, delta x squared over 2 times Cm plus 1 n minus 2 Cm n plus Cm minus 1 n, this term divided by delta x squared. This is approximately equal to delta t times delta x squared over 2 delta t, and this is an approximation for del squared c del x squared by our Taylor series approach, right? So basically Lax made it stable by adding a diffusion term. Is that very useful? Well, you can see that the diffusion term is proportional to delta x squared. So as delta x increases, the diffusion term squares. So that's one thing to remember. Plus the 2 delta t here, as time step decreases, you increase the diffusion as well. So going and writing again our B amplitude numerically, B to the delta t is cosine k delta x minus u delta t over delta x times I sine k delta x. So the scheme is stable only if b to the delta t is less than equal to 1, which amounts to the same as u delta t or delta x being less than equal to 1. So if CFL criteria is satisfied, then the Lax scheme is stable. Yes. Are we home free? Well, not quite. It turns out that if you look at the solution again of the exact solution as a propagating rectangle, the Lax scheme gives you basically a very diffusive solution. So we will see Lax Wendroff in the red line next, but just look at the black curve here. Comparison of the exact solution again of the thin blue curve with different numerical solutions of the advection equation. Lax scheme in the black curve and Lax Wendroff scheme in the red curve. So Lax tried to correct the Euler forward, and Lax Wendroff then tried to improve on the Lax scheme, which does improve the solution a bit here. The parameters are delta x equal to 0.2, delta t is 0.1, and u equal to 1. The initial condition at c equal to 1 is again this rectangle. Lax scheme exhibits strong damping and therefore an underestimation of the gradient. So the sharp fronts have been wiped out, and with time going from t equal to 5, 10, and 15, the peak is basically being wiped out and spread out in x. Okay, this is not very good at all. So Lax scheme is not really very useful. The Lax Wendroff scheme, which we will look at here, is an improvement on Lax. You can already see that here. So what did Lax Wendroff do to the Lax scheme? Basically, he added an intermediate step of c at m plus 1/2 delta x and n plus 1/2 delta t, called it c tilde, and that can be written as 1/2 of cm plus 1n plus cm at n minus u delta t over 2 delta x, cm plus 1n minus cm at n. So complicated steps, but not too difficult to understand. The attempt was to wipe out or try to remove the damping that is created by Lax in providing stability to the Euler forward space-centered scheme, but we have now gone from that simple form of the Euler forward centered in space, which was unstable anyways. So here now we can plug that back in to the previous equation and write cm at n plus 1 equals cm at n. So it's still like the Euler forward, except now we have u delta t or delta x times this c tilde at n plus half minus c tilde at m minus half plus and n plus half. So it is still kind of centered in space, but instead of using delta x, it's using half delta x plus also intermediate n plus half. So wow, that's defined here in terms of m plus 1 and n, so we are okay in that sense. It's not a matrix inversion that is needed. So we end up with an expression like this: cm at n plus 1 is cm at n minus u delta t over 2 delta x, and the centered in space, which is our original Euler forward. And then the Lax term is modified to u squared delta t squared over 2 delta x squared cm plus 1 n minus 2 cm n plus cm minus 1 n. So obviously we have again a diffusion term. So term d here is again written as delta t times u squared delta t over 2 times the central difference of the second order derivative, so d squared c dx squared. So approximately that's delta t times u squared delta t over 2. The diffusion term is now directly proportional to delta t. So delta t, the larger the time step, the diffusion gets larger. If you reduce it, then you get smaller diffusion. So you have improved the solution. You still need to satisfy the CFL criterion for stability. So looking again at the Lax and Lax Wendroff together, you can see that Lax was not very useful, but Lax Wendroff has made it much better, even though it still has the overestimation of the maximum and changing the shape, of course, and giving you this little wiggle in the back. So it is an improvement and stable with CFL, and it is recovered the peak. Definitely significant improvement on Lax. So not completely home free in terms of the choices of delta x and delta t, because you cannot choose them independently. They are related to each other. in reality. So nonetheless, in Lax and Lax Wendroff, the diffusion that is added numerically depends on delta x and delta t, so one has to still be careful about that in optimizing the spatial resolution time step for integration to optimize computational time and the numerical accuracy that you are seeking. So you're still going to have to worry about these few things, but it gives you a sense of the range of numerical methods, and this is not even close to being comprehensive. There are many methods that get evolved in aerospace engineering and so on, where very fast moving supersonic and hypersonic flows end up producing shocks which are like the sharp gradient we put in as rectangle in the exact solution, and the challenge is always to capture the shock and not smooth it out or not lose its identity and still have accuracy across the shock. We don't get too many shocks in our climate system, but you get sharp fronts, so we still need to capture those. So a lot of the methods that are developed in aerospace engineering, like shock capturing schemes, flux correction schemes, positive definiteness, monotonicity, and so on, are borrowed and brought into climate science, semi-Lagrangian methods and so on and so forth, which ensure that quantities like humidity don't go negative and so on. So it's a very vast field. We are getting a very short introduction. Next we will look at advection diffusion equation again, which we derived before, to see at some other numerical issues that arise when we make the equations more complicated than the simple linear advection equation that we looked at here. Okay.